All righty. So, last class we started looking at dependent motion. Okay. Um, the plan is to review today, continue working on some, and then if you have questions, work on the homework. Like questions, we can work on stuff together. Wednesday, I have a couple videos that I've made with some ropes and some pulleys, and we're going to go through a practice problem with like kind of a car being pulled with a rope up like a weight and analyze that. Okay, and then show you some. I have a six roped section of a pulley that I pull up and down on, and you can see what happens to the different rope sections and how fast they go. Okay, I don't know if anybody watched that one video that I did with the dependent motion. The rope each rope section will move at a different rate. Okay. Was it not posted on there? Hold on, let me check.
Homework 3 once.
I'm sorry. Someone should have told me. Homework 3. What homework are we in? We're on homework 4. Oh crap. I'm sorry. Someone should have mentioned that. Then you could have got started on it. Oh, did I? Oh, maybe. Okay, I'm putting it up right now. All right, homework 4 is up. There we go. We'll look at that after we review. Okay. Okay. And then Friday we'll review, and your second exam will be Monday. And it'll just cover this homework and last homework. So just normal and tangential, relative, and dependent motion. Okay. Then next Wednesday we can finally look at more advanced Newton's second law. So, okay. So here is just a review. We started looking at dependent motion, which relates two objects or more to movement. All right. And in this case, what we had is two different ropes, and each rope section is constant. Okay. The rope, we're assuming it doesn't stretch. We're not adding ropes. Okay. The total length of the rope always remains constant. And if you figure out the lengths of the rope that are changing, all right. Can you hear me now? Let's try this again. Okay. That was strange. It completely kicked me out. Did it kick anybody else out? Or is it just me? That's weird. All right. Keep moving. Um, let's look at this. So we also looked at when you have motors. Okay. So the way to do this is when you have a motor, what you do is you pick a point away from the motor, okay, and you can do dimensions like this. Now, what we did up here was we defined the datum up here. Okay. Now, what you could do in this case, and I'm going to maybe copy this. Can we copy just that? Let's see, I might have to do it over here. Yep, okay, that's fine. Shoot. Hold on, let me undo. Let me paste it way over here. There we go. And move it right there. And then zoom in. What you could do is you could still pick your datum here. Okay. And then you would have these three sections. Okay. Then what you could do is you could pick your data, another datum here, and go this way. And then this point right here, you could label as SM. And these would be SB, SB, and SB. Why? Because this section right here, that's an orange, is a constant. That never changes. So you don't even technically have to worry about it. All right? So you would still add these up and you would get the same equation that we did last time. So there are multiple ways you can look at a particular problem and define your data. And so you just have to go and pick one. You make sure your datum is on a fixed position though. Don't put it on a movable section, okay? All right. And we looked at this one and I showed you kind of the long way and then the shortcut way where if you cut above the movable pulley sections, count the number of sections, that will give you your ratio, okay? All right, so let's look at this. We need to finish and then I'll look at other problem that we were right at the end. Okay, so here is a truck that is pulling a log to the right, all right? And let's pick the datum right here. It's a fixed location, all right? Yeah, these should be on OneNote. Yep. It's in week 4, day 3, because we're still finishing the packet. Is anybody else using OneNote? Can you find it? Let me know if you can. I'm not sure. It should be on there.
You're still underneath week 4, correct? Yeah, week
Yes.
4, day 3, yep.
Yeah, right there. Week 4, day 3. Yep.
Yeah, I can
Yep.
see it.
Okay. Yeah, check that, Anthony. Okay. So what we can do here, okay, I'm going to show you kind of 2 different ways, all right? One way is kind of the wrong way, okay? All right, now I want to make sure I do this right. I guess I can do that, sure. So let's label from here to here as SB. Okay. Then I'm going to label right here to this point right here as ST, the truck. Let's do capital T. I'm going to zoom right up on that one. And this B. Maybe I can't. Oh, it froze. B. So what do we do? So we labeled, we picked a datum. It's like a station point. This truck is kind of acting as a motor. Okay. And We picked a point on the left of the datum. And why don't I show you something else you could do? Oh my God, sorry, my computer's acting up. Paste it right here. Oh, there we go. Let's make it a little smaller. We could pick our datum here still. And we could actually pick this distance and call it S of the truck. And we could do basically SB. Okay. So you could pick on the left side, that's fine. Okay. Or you could pick the right side. Now, no matter which decision you make, what you have to realize is in each section, I'm going to label these green. Okay. So basically all of this, and all of this. Those green sections are what you have to figure out the dimensions for. Okay. Does that make sense, everyone? So pick a point on the left or the right side and then identify which sections of the rope from that point on to the end you have to look at. Okay? So it doesn't matter which one you do. You just have to make sure you identify the rope sections. Okay? Now, that's all I wanted to show you up here. The way I would do it is I'm going to show you down here. Is again, I would pick this as my datum. I like to pick basically a point that's off from a pulley. And I label this the point, okay? Because I don't like to, I like to make sure I distinguish between that point of the motor and any other point that could be in my head. Then I need to find this dimension, I need to define this and that. Okay? So the way I would do it is, again, I would label from here to here as SB. Okay, I'm going to zoom right in here. And let's do purple. Right here, that section of rope is SB minus S of the truck. Okay. That's just fine minus that point on the truck, that dimension. Now those other 2 points, I like to define these distances as A. So this distance right here is A. So these 2 green sections, and I'll put an arrow here and I'll put it up to here, we'll do plus. There's 2 of them, and it would be SB minus A. And that equals a constant. So you end up with 3SB minus st minus 2a equals a constant. Then we can take the time derivative, 3vb minus vt, we get 0 equals 0. Oh, hold on, gotta grab the baby. Knock down the trampoline. So we end up getting 3vb equals basically vt. Okay. Are there questions on this? Does that make sense? Now, hopefully you can still hear me. Let me know if you can't. If you noticed that, okay, good. Thanks, Joseph. All my arrows are pointing left. Okay, I can kind of assume that's my positive direction. And that's why sometimes, like, if VB is moving to maybe the right, okay, you're going to get maybe different signs, okay? And that's all based on your datum, okay? So you got to make sure you identify your datum, what directions you're having, and then if it's a negative or a positive, then you kind of have to realize that. For now, just do what you're doing here. When we get to forces, you'll see how that all works in, okay? So as long as you understand, here's a datum, pick my dimensions, and go from there. And again, I like to pick, if you notice, top picture, I didn't pick my point, if it'll load, there we go. I don't like to pick my motor point or truck point along the same location as another pulley. I like to make it off slightly so I know there's a difference, okay? All right, cool. Okay, so now let's go where I'm still in week 4. We'll go to the untitled page, okay? And it's got this problem on it. I'm going to review this problem, okay? We probably do the derivative again. Okay. So we have a girl at sea stands near the edge of a pier and pulls in the rope horizontally at a constant speed of 6 feet per second. Determine how fast the boat approaches the pier at the instant the rope is 50 feet. All right. So the cool thing is, like, we can do this and find accelerations, and then next chapter we do forces. We can find the tension in the rope based on its movement or its acceleration, and then you can go and size that rope if you want. Okay. So what do we do? Well, I'll start right here, and then basically what I'll do is I'll redo this for you. I'll just put this in a squiggly mark. I'll put week 4. And then I'll do it again down here for week 5, okay? So the length of the rope, we have this orange section, okay, which we defined as HXC, okay? Then we define this purple section as this right here. 8 squared plus XB squared, take the square root, okay? So the total length of the rope is constant. And now in order to figure out how things are, we just take the time derivatives. Okay? So let's go over here and do this again, week 5. So let's call y 8 squared plus xb squared, and I raise it to the 1/2, which is the same as the square root. So dy dt, if we want to take the derivative of y with respect to time, okay, we have to use the chain rule because we don't have time involved in here. We technically do because xb is a function of time. But if you have this, you just take the derivative of xb, the derivative of y with respect to xb times the derivative of xb with respect to time. He's getting into everything. So let's take this derivative, dy dxb. I want to make it green. So we have 1/2 8 squared plus xb squared to the minus 1/2. Then we times the derivative on the inside, 2xb. That's the derivative of that. Okay? And the derivative of dxb dt we just can define as vb, because that's just position over time taking the derivative. So dy dt equals the 1/2 and the 2 cancel. So you get 8 squared plus xb squared to the minus 1/2 times xb times vb. And so now this term goes into here, or takes the derivative. So let's plug this in. So the derivative, let's just write this over. Otherwise, you're probably going to go back in your notes and you're going to miss it. Is that. Go ahead and write that. I'm going to grab the baby. Hey. Wow, you are crazy. You are on the move. Oh.
Where did the 2 go for the 2 at B?
It cancels with the 1/2.
Oh, okay, yeah. I see now.
Right here.
Yep.
Oh, that was a little laggy. It took a while. So do we have everything? Do we have VC? Yep. We have 6 feet per second. XB. Do we have that? We could find that. Yep. And you could rearrange. So you could solve. So basically, you need to find XB based on the AB is equal to 50 feet. That's easy. Just square root of the squares there. So you can actually plug everything back in. Okay. I actually don't even know if I did this properly. Yes, I did. So XB, square root 50 squared minus 8 squared. So you get 49.4 feet. And the reason I'm doing it over here, because I'm going to take the derivative again to show you acceleration. Then you plug it in, and VB becomes 6.08 feet per second. Hey. Questions on this?
Sir, how did you get 6.08 feet per second?
You just rearrange, right? So this is 6 feet per second plus 8 squared plus 49.4 feet. I'll just put the square to the minus 1/2 times. Let's see, it should work. 49.4 plus 8 squared.
Got it.
You get it? And it comes out actually negative, right? Yeah, there you go. Yeah, because it's going the opposite direction. Other questions on this one? Okay, now let's take this box equation and then how would you find AC or find the derivative again? That's going to relate accelerations, right? So the first term is easy. That's AC plus. This next term is the tricky part. Why? Because there's 3 terms. And I'm going to do it over here. I'm going to call y, again, 8 squared plus xb squared to the minus 1/2. So what you have to do is you got to take the derivative of y with respect to t. So the derivative of the first times the second and the third times xb plus vb plus the derivative of the second times the first and third. So vb times y. Then it's the derivative of the third times the first and second times y times xb equals 0. So you have to use the product rule 3 times because there's 3 functions in this. Okay, the first function is y, which is this term. The second function is xb, and the third function is vb. And why am I calling them functions? Because each one of those terms has got a variable that's a function of time. Okay. So this is the derivative of the first. This is the derivative of the second. This is the derivative of the third. All right. 1, 2, 3. What do you have to do to find the derivative of the first? dy dt. Can someone tell me? So how do you find dy dt of that function? What math rule?
Isn't it taking the natural log?
Nope. Nope. What do we do up here?
Yeah,
What
chain rule.
is chain rule? Yeah. No partials. Nope. Nope. These are derivatives. You have to do the chain rule. So use chain rule, like we did above. So you got to. So if you're going to find acceleration, you have to do the product rule and the chain rule. Do you see how much math is involved now? So it's dy dxb times dxb dt. I'm pretty sure there's a problem on the homework that deals with this. Find accelerations. Okay. So I have just covered everything there is for dependent motion.